I think it may as well kick off. Yeah, cool. Hi, I hadn't planned to talk about anything here, but I spent a while this afternoon coding up some Scala, a Scala implementation of selective applicative functors. I find them interesting, so I thought I'd give an introduction to them here. My name is Thomas Sutton. I'm from Sydney. Thank you to anyone who's an organiser in here for an excellent conference. So, selective applicative functors are described in this paper called Selective Applicative Functors, which I don't know if it's been accepted yet. I think it might still be under consideration for the International Conference of Functional Programming this year. It's by 4 people whose names you might recognise, who are luminaries in the functional programming, typed functional programming world, particularly Haskell. This paper is written in Haskell, and there's a library in Haskell that implements selective applicative functors, and they've also implemented them in OCaml, and there's a library of Coq proofs of correctness and the laws and so on and so forth. I haven't prepared slides. I thought I'd just show the paper and then dive straight into some Scala code so that you can kind of try and get a feel for what these are useful for. It might be, though, useful to know what the purpose is. So most of us are probably fairly familiar with the ideas of effectful programming in functional languages and having functors and maybe applicative functors and monads. At the level of functor, we have an atomic effectful computation. We can run it, we can map a function over it, but we can't combine 2 of them together without knowing in detail what the particular types are. If we did want to try and write a function that took 2 values of some functor type and combined them, there's no code that you can write there in a type-safe language. If you want to combine 2 effectful computations, you need a more powerful interface. So one of the venerable such interfaces in typed functional programming is the applicative functor. So that lets us take one effectful computation and run that, and then take another one and run that, and then combine them together. That's very useful, but if you wanted to write a program that has dynamic effects, so if you want your program to read in from the user, how many missiles should I launch, and then launch that many missiles, you can't write that sort of program with applicative functors because they're static. The shape of the effect that they have must be known at compile time. If you want that more powerful programming model, historically we've had to go to monads. The problem with monads, though, is that you can't statically analyse them like you can with applicative functors. If you call a flat map operation, there's a function that decides what to do next, and you can't, at compile time, know what that function is going to do. Maybe it will look at a database. Maybe it will consider the input that you've given it. It's an entirely dynamic runtime process, which makes it very hard to statically analyse. Selective applicative functors fall into the middle ground in between applicative functors and monads. So they require that you statically declare all of your effects at compile time, like an applicative functor, but they let you choose at runtime whether or not you will execute some of those effects. Possibly, if you're a Haskell programmer, you might be familiar with the opt-parse applicative library for parsing command line options. That uses the applicative functor interface to help you describe the command line arguments that you want to accept, and then it can parse them at runtime, but it can also generate help text. Generating help text is a really good example of the case where you need to be able to statically analyse this value. You need to be able to, without executing it, to know what are all of the possible things that can happen here. What arguments do I accept? How do I validate them? Maybe my program's like Git and has a very complicated, complex command line parsing setup. That's exactly the sort of situation where this selective applicative functors abstraction can be helpful. So I hope that's given you a bit of an intuition for what they do exactly. well, approximately, not exactly. I highly recommend reading the paper if you're familiar with Haskell. If you're not familiar with Haskell, I recommend becoming familiar with Haskell and then reading the paper. There are many more examples and much more theory in the paper than I'm going to bother talking about today. But it's a very enlightening read. So I'll jump now into some Scala code which implements this. I've just sketched out functional programming interfaces in Scala today, so this isn't based on cats or Scala Z or anything else, but I hope that this can demonstrate the shape of the interface. So Functor looks like it usually does. I'm a Haskeller, so I spell map, fmap, sorry. So functors are the types that are atomic effects. We can't combine them. Using this interface, there's no way. The only thing we can do is take an effect and fiddle with its insides. We can't combine these things together. That should be fairly familiar to everyone. The next most powerful interface is the applicative functor. So this one, we can make new atomic values with pure. That should be hopefully straightforward. And we can also combine the two things together. In some interfaces, so Scala Z with all of the funny syntax turned on, or Haskell, the sort of code that I'm talking about here looks very straightforward. We wind up with something like that, where we're taking two effects and combining them together, putting them in a tuple, or throwing away the result of the second one, or so on and so forth. But I hope you can understand, you can see that this interface allows us to do that. It allows us to take some effectful computation with a function inside and another one, and then run them both and combine the results. If anyone has any questions at any point, interrupt please, because this is going to be quite short. So historically then, not historically, prior to this paper then, the next interface, if that wasn't powerful enough for you, you had to go straight to monad. And monad gives us the flat map operation where we can take some effectful computation, we can execute it to get the value inside, and then based on that, we can do whatever we like, produce any other effectful computation we want. And this is the root of where the dynamic properties of monad come into play. This is the reason that we can't analyze a monadic computation, because you can't look inside that function in the compiler in abstract and decide what it's going to do, determine what it's going to do. The only way to do that is to execute it. And that means you need to know what the user input was, and there's no way you can possibly look into the future and make that call. So in a general purpose programming language, this is basically where we stop. If you've got this far, then you basically need to just do the code correctly yourself. The compiler's not going to be able to help very much for those static properties. So what does it look like to stop halfway? What we might do is we might look at this A in the effect and say, well, if we did want to make a decision whether or not to do the next step, we'd have to scrutinize that A in some fashion. We could say, well, let's just make it bool. We're just going to have some sort of functor that has an operation built in that magically knows how to handle bools and make that decision with a boolean. Or we could use a coproduct. As we've seen earlier in this room, they're very predictable and they're slightly more useful. With a boolean, you will have the boolean blindness problem, where the boolean is true, the boolean is false. You need to keep track of in your head which case is which, and you need to get it right when you write the code to process those. If we instead use a coproduct there, then we can have A for one case and B for the other case, and we can't accidentally process them with the wrong implementation. So that's in fact what they did do. They used either. And the other thing we might do is, the problem here is that the arrow is outside of the effect. The function is deciding what sort of effect to do. So that's what's causing the problem with static analysis. So if we take that and move it inside the effect, then that makes the effectful computation available for us to analyse. So that leads to an interface that looks like this. The first argument is an effectful computation that has an either inside. And the second argument is a function that can process that. If you're thinking, well, when I first heard of these, I thought that the obvious interface would be to have something like the fold method on either, but with some functors in there. So we would take an either A, B, and we would take a function that handles A's, and we would take a function that handles B's, and we would get an end result. In the paper, and they explain why they chose this particular interface. So what we do here is we'll run the first argument to get the either out. If it's a right with a B inside, that's cool, that's our answer. There's no work to be done. On the other hand, if there's an A, then we'll run this second effect to get the function out and then apply that to the A. So our effectful computation that produces this gets to decide whether or not the next step will be run. If it wants it to be run, it can return a left of A, and if it doesn't want it to be run, it can return a right of B, and that's just going straight to the end. So if you're thinking about a lot of looping logic where we're counting down to some result, or we're do while with some condition, this is the similar sort of logic here. We're skipping the next step or performing the next step. So what can we do with these sorts of things? There's lots of things. I've already mentioned parsing, so having static parsers that we can analyse and produce help text is one example. In the paper, they describe some simulation software that they write to analyse the properties of instruction set architectures. So they will write a small program in a selective functor for each instruction, and then they can analyse it to determine what does it read, what does it write. They can generate diagrams, flow diagrams and block diagrams of the CPU microarchitecture for that instruction. It's very detailed, and I highly recommend seeing some of the case studies in there. They also describe using it in a build system for OCaml, where the effects are things like checking a file and building the file based on its dependencies and those sorts of things. And they also describe application to Facebook's Haxel system, which is a highly parallel system that they use for detecting inappropriate behaviour on Facebook, advertising and harassment and those sorts of things. In that context, this allows them to continue using Applicative, which in their system is gets executed in parallel. It doesn't force them to go to monad, which must be executed sequentially. So that allows them, in their case, to write programs that have some degree of dynamism. They have selective functors to make choices to do something or not do something, but they get to keep being parallel, automatically parallel. It doesn't force them anymore to go to using a monadic interface, which must be not parallel, the opposite of parallel, in a straight line. Anyway, so in the paper, they use this single method, the select method, to implement a wide range of combinators. I'm just going to show two of them. And these are implemented in terms of the select operator. This code is a little bit awkward. I assume Dotty will help fix some of the type inference stuff that's going on here. So we can implement a branch operator, which is what I was expecting would be the default interface, personally. We have an either AB and then we can turn an A into a C and a B into a C, and we just call whichever one we need to. So that's the interface I was expecting when I first heard of these things. But as you can see, we can just define it in terms of the select operator. One thing to note, though, is that we need to be careful with this, implementing this, to make sure that we implement it correctly. When you call branch, you should execute exactly 2 effects. You should execute the first one exactly once, and then you should execute either the left hand or the right hand. So it's moderately easy to implement this incorrectly, so that you execute the first one twice, for example. So it can be a little bit tricky to get these right. The other combinator is if. So this is where we do take a boolean instead of an either. And I mean, it's obvious in the interface, you can quite easily get these wrong. You can quite easily put the else effect in the then case and the then effect in the else case. The way this is implemented is we take the effect with the boolean inside, and we just fmap over it a function bool, which I've just defined down here, that if it's true, return left with something in it, and if it's false, return right with something in it. So it's the very obvious translation from boolean into the coproduct of 2 units. So once we've done that, then we just convert our yes and our no into functions which accept a unit and throw it away and return the answer. And then we just use branch. So there are many, many more combinators than this in the paper, and they go through and describe a lot of them in some detail, and make some really good observations around things like the integration with Haxel, where they have conjunction and disjunction operators that continue to maintain the lazy parallel semantics that they need to get high performance in their application. So that's a sketch of the interface. So I'll just introduce 2 implementations of it. Again, they come from the paper, and they're illustrative rather than something that anybody would have a concrete use for in production. So I mentioned static analysis a lot. That's rather the point of some of these interfaces, and that's what the examples are. So this is the const functor. It's very common in Haskell. It's a little bit common sometimes in Scala Z. It may or may not be familiar, so I'll just, if it isn't, please interrupt me, because the next step won't make much sense if you don't follow this. So const is a case class. It takes 2 parameters. It's a lot like the const function. So the const function takes 2 parameters. It returns the first one and ignores the second one. So it's a constant function. No matter what you give it, it returns the same answer. Const is the same, but as a data type. It's got a t inside of it. It ignores the second type parameter always. That's the type parameter, which is the hole in the functor instance. So this is a data type that has something inside it, and you can do functor things to it. You can fmap it, you can app it, you can pure it, and it will just ignore the thing that you give it, always. The wrapped value stays constant. So what might we use this for? And you can see that here. So fmap, so if we have a constant with a in it, well, the answer is constant with a in it. We just ignore the function that we're mapping. The same with app. So what might we use this for? In the paper, they use this, or 2 renamings of this, to keep track of effects that are being executed, or that could be executed by a program. So our goal is to statically analyze. We can't statically analyze exactly anymore, because we do have this selective functionality. It can decide that, no, I'm going to skip that one. So we're not going to have an exact analysis, but we can have approximate analysis. So we can have similar definitions to the const functor called over and under. And if you look at them, under, I mean, it's const, just renamed. And over is const renamed as well. The only difference between them is the behavior of their type class instances. For fmap and pure and app, they act exactly the same. On select is where we have the difference. In under, we would like to collect up a record of all of the effects that will definitely be run. The program may well run more effects when we run it, but we're going to collect everything that will definitely run so that we have an underestimate of the effect of the program. On the other hand, over will log every effect that the program could run. It's entirely possible that no execution of the program will produce all of those effects, but it is everything that could possibly happen. So what we can get then is two different analyses, approximate analyses of the same program. One of them is an underestimate, one of them is an overestimate, and somewhere in the middle will be every single execution that can possibly happen. So what might this look like? It would look like I've closed that window. Program. So consider these few actions that we've got. We've got some atomic actions. We can check whether there is an asteroid heading for the Earth. And we can call Bruce Willis, and we can send Bruce Willis into space with a nuclear bomb, and we can declare that the world is safe. So we can combine those together using if. So that's the operation that we defined in terms of bool with select. So we can write a program that, for instance, checks to see if there is an asteroid heading for the Earth. And if there is, we're going to call Bruce Willis, and then we're going to send him into space with a nuclear bomb. And if there isn't an asteroid, well, we'll keep looking. Because the world may be safe today, but tomorrow that guy will still be making bad films. So that's our program. And we would like to be able to analyse it and tell statically, to the best extent that we can, what effects it is going to have. So there's a bit of noise in here that's kind of hiding what's going on. So you've probably noticed I've used const here. I don't want to use const. I would like to use my two different functors, selective functors, so I can analyse the program. So in Haskell, I would turn on a whole bunch of language pragmas and have this just work in various ways that Oleg, who has already been mentioned before in the logic monads talk, made clear a long time ago, but I can't, unfortunately. What I've done instead is used a natural transformation that will convert const into some other thing. So I'm just using the same program here, and I'm saying, hey program, please convert all your things into over, and hey program, please convert all your things into under. It's just machinery, it's not actually part of the selective functors stuff. I probably shouldn't even have mentioned it. So the same program, I'm running it under either, under over and under, and then just printing out the results. So, well, there's the answer. So we can wait for SBT. Yeah. Right. So we've got two different analyses of the program that give us a list of all of the things that will definitely happen and a list of all of the things which could possibly happen. There are more precise analyses we can do, but this is a very, very easy one to do. So for instance, no program will ever run and actually produce all 4 effects. This trace is actually impossible for our program. So we've slightly overestimated what could possibly happen. What we would ideally like to have, the exact analysis would tell us that we either run or check to see if there's an asteroid coming, then call Bruce Willis and then launch him into space, or we check to see if there's an asteroid coming and then we know that the world is safe. So those are the 2 alternatives that can actually happen. But that requires a lot more machinery, and this is very quick and easy, and we can do it in our own programming language. That's probably all I've got to say. There's a lot more detail in the paper, and there's a lot more theory in the paper. If anyone has any questions, you're welcome to ask them. No? Thank you very much.